Here's an interesting physics problem that was given to 9th grade students sitting the Romanian National Physics Olympiad back in 2016. So this was part of the second question out of 3, and more specifically it was problem 2C. So problem 2 had 3 parts, A, B, and C, and this is actually the only part of the question which deals with mechanics. The previous 2 parts, A and B, were not related to this and were kinematics related. Now, if you'd like to see anything similar to this on the channel, any particular subjects from any past years, let me know down in the comments. So let's read the question and then let's try to figure out how to solve it. As usual, this has been translated with ChatGPT. The translation is pretty good, and this is the diagram that the students had in the paper. So for parallelepiped bodies, so I think this is like for prismatic bodies, like 3D rectangles essentially, resembling small bricks, with the masses indicated in the diagram, are connected to each other by inextensible and massless strings. So pretty standard so far. Under the action of a constant force F, which acts horizontally on the body with mass m, as we can see in the diagram, the system of the 4 bodies moves to the right. The coefficients of friction between the first 3 bodies and the horizontal surface on which they move are known. So we know mu1, mu2, and mu3. So mu1 is 0.4, mu2 is 0.2, and mu3 is 0.1. And immediately after the action of the force F has ceased, so when F stops existing, essentially, the 3 connecting strings between the bodies remain under tension. And the question is, what's the minimum possible value of mu4, which is the coefficient of friction between the body M4 and the surface, so that the bodies continue to move? Okay, so we know all the masses. Well, we don't know the values in kilograms, but we know the relationship between the masses, and we also know 3 out of the 4 friction coefficients. So let's try to understand what's happening here. So there is a force applied and the system starts accelerating, and then the force stops being applied and the system is going to be decelerating. And it seems like the only part of this process that we are interested in is the part when the force disappeared. So let's do a free body diagram of the entire system and you'll see why that's relevant. So if I draw the floor and the 4 bodies decelerating, we're going to see something like this. So we have M4, we have M3, we have M2, and we have M1. Right, and at this point, the only force or the only forces in the horizontal direction that are acting on the system are the friction forces. So we've got, let's write down the masses. So we have M, this is 2M, this is 4M, and this is 8M. And this is the friction FF4, this is going to be FF3, this is FF2, and of course this is FF1. Okay, so with this in mind, we can actually find the acceleration of the system. So the system is clearly going to accelerate, so I'm just going to write the acceleration to the right, although we all know it's going to be to the left, but I'm choosing right as my positive direction, so yeah, I'm putting the acceleration like this for now. So what we can then say is that we have minus FF1 minus friction 2 minus F3 and minus FF4 equals to the total mass of the system. So that's going to be M plus 2M plus 4M plus 8M times the acceleration, like this. So we can actually figure out what the acceleration is, not fully because we don't know what the fourth frictional force is, but we'll get to a certain point and we'll see what we do afterwards. So the friction, so all four frictions are kinetic frictions because they're, the objects are sliding. So FF1 is going to be equal to mu1 mg. FF2 is going to be equal to mu2 times 2 mg. Then the third is mu3 times 4 mg. And then FF4 is going to be equal to mu4 times 8 mg. Okay, so normally I don't recommend plugging in the values at the beginning of the question, but I would do it in this case because otherwise the problem is going to get like all the notations are going to be a bit long, and we just have to sub in the friction coefficients, which yeah, those are just some coefficients that are constant. So I'm just going to plug them in one by one. So this is going to be 0.4 mg. This is going to be 0.2 times 2 mg, which is the same. So that's another nice thing, that the first and the second friction forces are equal. This one is also going to be equal to 0.4 mg. And the last one is the unknown. So this is 8 mu4 mg. And our goal is to find what mu4 is, or what's the minimum value of mu4. So if I try to find the acceleration from the equation above, I would get that acceleration is equal to minus, and then I have all the friction forces added up like this in the numerator, and then everything is going to be divided by the sum of the masses, which is, so this is 3, 7 plus 8, 15 m, like this. So this is going to become equal to minus, so we're going to have 0.4 plus 0.4 plus 0.4 mg, which is 1.2 mg, plus 8 mu4 mg over 15 m. So this is the expression of the acceleration or the deceleration of the system after the force F has stopped being applied on M1. So how do we actually find mu4? Well, what we're going to use here is the fact that after this force stopped, the three connecting strings remain under tension. So this is the key fact that we're going to use. So what I'll do now is I will draw the free body diagram of each individual object. So for M, we have the friction, of course. So we have FF1 acting backwards, and we also have the tension in the first string, which is T1, and we just we know what the acceleration is, or we have an expression for the acceleration. So we can write that minus T1 and minus FF1 is equal to MA. So this means that minus T1 and minus mu1 mg is equal to mass times acceleration. So this is going to be well, this thing essentially. So this is minus m times 1.2 mg plus 8 mu4 mg, everything divided by m, by 15m. And what this becomes is T1 plus mu1 mg, or I'm just going to write it 0.4 mg, is equal to 1.2 mg plus 8 mu4 mg over 15. And of course what I've done here is I multiplied everything by minus 1 to get rid of the negative signs. So we have that the tension T1 is going to be 1.2 mg plus 8 mu 4 mg over 15 minus 0.4 mg, and then we amplify everything by 15, and we get that T1 is going to be 1.2 mg plus 8 mu 4 mg minus, so 0.4 times 15, this should be equal to 6 mg, and this is divided by 15. Okay, so we can rewrite it as 8 mu 4 mg minus 4.8 mg divided by 15. So one thing that we know for sure is that the strings, including this one, T1, is under tension. In other words, this tension is strictly positive, right? It cannot be zero. So if we solve for this, if we solve this inequality for mu 4, we essentially get that 8 mu 4 mg is bigger than 4.8 mg, and we can cancel out the weights. So mu 4 is bigger than 4.8 over 8, which is 0.6. Okay, so in other words, for tension T1 to be, or for the first string to be under tension, the friction coefficient mu 4 has to be at least 0.6. And if you got the idea where this is going, we have to do the same thing for the other two strings as well. So the next thing we're going to look at, the next string we're going to look at, is going to be the one connecting 2m to 4n. So we're going to look at this one now, and we're going to need the calculator. So let's draw everything that we know. So we've got T1 acting this way, we have T2 acting this way, and we also know there's friction, which is F2, like this, and of course we know the acceleration using the expression that we got earlier. So we can say that T1 minus T2 minus 0.4 mg, I'm just going to write it straight away, is equal to the mass of the second object, which is 2m, multiplied by the acceleration being what we see here. So that's minus, make sure to copy it correctly. So I'm going to put g in front, and this is going to be 1.2. So 1.2 plus 8 mu 4 plus 8 mu 4 divided by 15. Okay. We also know the expression for T1 as well. So let's try to rearrange this and find T2. So T2 is going to be equal to T1 minus 0.4 mg, and then it's going to be plus 2 mg, and then 1.2 plus 8 mu 4 over 15. Okay, so what we should do with this is we should plug in the value of T1. So T2 is equal to, T1 is somewhere here, so this is T1. So 8 mu 4 mg, 8 mu 4 mg, minus 4.8 mg over 15, minus 4.8 mg over 15, minus 0.4 mg, and then we have plus, and what I'll do here is I'll just multiply straight away. So that's 2.4 mg plus 16 mu 4 mg over 15, like this. Of course, we'll multiply this by 15 as well, and we're gonna get an expression for T2, which is going to be 8 mu 4 mg minus 4.8 mg minus. So 0.4 times 15, this is going to be 6 mg again. And then we have plus 2.4 mg plus 16 mu4 mg divided by 15. So T2, if we combine all the like terms together, we should have, so 8 plus 16, so that should be 24 mu4 mg. And then we have minus 6 minus 4.8 and then plus 2.4, so that's minus 8.4 mg over 15. Okay, so this is T2. So that's all good. And we know that this should be positive as well. So we can rearrange and get 24 mu4 mg should be greater than 8.4 mg. So from this condition, we get that mu4 should be greater than 8.4 by 24, which is going to be, so 8.4 over 24, so that's 0.35. So we got a different value, which is fine. So we'll try to find the tension in the last string, and then we'll try to understand what's actually happening here. So for the next free body diagram, we're going to look at 4m, and we're going to look at the tensions as well. So we have 4m like this, and then we have one tension this way, so that's T2. We have one tension this way, so that's T3, and we also have the friction, and of course we have acceleration like this. So we can say T2 minus T3 minus 0.4 mg is equal to 4m multiplied by the acceleration, and the acceleration is this. So we have minus g, and then I think it was 1.2 plus 8 mu4 plus 8 mu4 divided by 15. Okay, right. So we have to find T3. So let's rearrange, and we get T3 is equal to T2 minus 0.4 mg plus, and then we have 4 mg, and then 1.2 plus 8 mu4 over 15, like this. Right, so T2, we got it on the previous page, so that's 24 mu4 mg, and then that is minus 8.4 mg, and I think that's it, and that's over 15, minus 0.4 mg, and then I'm going to multiply the 4 mg with the numerator, so we get 4.8 mg plus 32 mu4 mg over 15. Right, so again, I'm going to multiply 15 here, and we're going to get something similar to T2. So we get this bit, and then again we get 0.4 times 15, so that's 6 mg plus 4.8 mg plus 32 mu4 mg, like this. And this is divided by 15, and this should be equal to, so we have 24 here and 32, so if we add those up, we should get 56 mu4 mg, and the other term should be negative, so that's minus 8.4 minus 6 plus 4.8, and this gives 9.6 mg over 15. Okay, so this here is the third tension, which of course should be positive. So if we solve, we have 56 mu4 mg should be bigger than 9.6 mg. the mg's go, and mu4 is bigger than 9.6 over 56. And this is smaller than the previous values, and it's about 0.17 roughly. Okay, so let's think about it. So for T1 to be greater than 0, so for the first string to be under tension, we got mu4 should be bigger than, I think it was 0.6, I believe, which is this one. Okay, for the second tension, so for T2 bigger than 0, mu4 has to be greater than 0.35, so this value. And of course, for T3 to be greater than 0, mu4 has to be greater than 0.17. So obviously mu4 cannot take all three values in the same time, so we have to think, okay, which one is the correct, which one is the true minimum value? And the answer, of course, is this one, right? It cannot be any other value, because if you want to think that mu4 should be 0.17, then okay, T3 will be positive, but T2 and T1 will not be able to be under tension anymore, because for T1 and T2 to be under tension, the fourth friction coefficient has to be either 0.35 or 0.6. Alternatively, if you think that the friction coefficient should be 0.35, this value satisfies the condition for both T2 and T3, but it doesn't satisfy the one for T1, because T1 needs a mu of 0.6. Therefore, the only correct value, so the minimum mu4 is the maximum out of the three values, which is 0.6. So mu4 should be bigger than 0.6 for all three strings to be in tension. And that's the end of the question.